This session focuses on TCP segment header. As you know, the TCP segment is the data unit exchange between two different TCP entities. The one end of that is the sending end to the receiving end. So every segment begins with a fixed format 20 byte header. So the first part will be a fixed part, that is a 20 byte header. Followed by that, there can be a number of or set of header options will be there. After that, there can be some data part, and the size of the data part will be maximum of this much minus 20 minus 20. So 120 is actually for this IP header, and the second 20 for the TCP header. So 40 bytes should be reduced from this maximum capacity, that is 65535. So this much may be the maximum data size of a segment. And segments without any data are legal and are commonly used for acknowledgement. So the data size may be 0. In that case, it is actually some control purpose like acknowledgements and all. And this is the format for TCP segment header. We have a source port, destination port, sequence number, acknowledgement number, a set of flags together with TCP header length, window size, checksum, urgent pointer, and options are there, variable length option field, and data, that's also optional. So we will see one by one which are the different fields and their purposes. So first field is source port and destination port numbers. Those are actually local endpoints of the connection. So TCP port number plus its host IP address, that forms a 48-bit unique endpoint, that is a socket, right? And the source and destination endpoints together identify each and every connection. And usually this connection identifiers is called a phi tuple because it consists of 5 pieces of information. What are the different pieces of information? The protocol used for this connection, that is TCP, source IP and source port, these two, and destination IP, destination port. So 5 different pieces of information together forms a connection. And this next two fields are sequence number and acknowledgement number. Acknowledgement number specify the next in order byte expected. Okay, remember that it is not the last byte correctly received, but the next in order byte expected. That byte number will be the acknowledgement number. It's a cumulative acknowledgement because it summarizes the received data with a single number. So if acknowledgement number is X, means up to X minus 1 is received correctly. Next I am expecting X. That is the meaning of this acknowledgement number. So it's cumulative acknowledgement. It does not go beyond lost data. So if a data is lost, any data receiving after the lost data, it won't be acknowledged. That is, just for example, suppose all the bytes up to X is received correctly, X plus 1 is lost. In that case, if X plus 2, X plus 3, etc. are received correctly, even then the acknowledgement number is X plus 1. I am next expecting X plus 1. Such a acknowledgement number will be sent again and again until it receives this X plus 1 correctly. That is why it is said that it does not go beyond lost data. Both are 32-bit numbers. Both sequence number and acknowledgement numbers are 32-bit numbers because every byte of data is numbered. That is the thing here. So every byte is given a unique number. So that much length there should be the sequence number, right? That is why we are using a 32-bit number. And the next field is TCP header length. It tells how many 32-bit words are contained in the TCP header, only the TCP header length. And it counts the 32-bit words, how many 32-bit words are there. Just for example, the length of this header is 64. The value in this TCP header will be just 2. This information is needed because the option field is of variable length. So that header is 2, right? Yeah. Why we need such? If the header field is actually fixed, there is no need of a header length. But in case of a TCP, header field contains some options. It's and variable length options are there. So totally, what's the length of this header? And the purpose of this field is actually to indicate where the data starts in the segment. Actually, if we are specifying the length of the header, that is actually the offset to the data, the first byte of data, right? Yeah, in effect, both are same. That is why the length field is used. It actually indicates the starting point where the actual data in that segment starts. Okay. So up to this is over. Now a number of fields or number of bits are not used. Then we have 8 different flags. We will see what are the purpose of these. The first 2 flags are CWR and ECE. These 2 flags are actually used to signal congestion when ECN is used. Okay, that is CWR stand for congestion window reduced and ECE stand for explicit congestion notification echo. So these 2 flags are used when ECN is used in transport layer. ECN means explicit congestion notification. So and the specification for this explicit congestion notification is given in RFC 3168. So in case of internet, every standards and specifications are published as a set of requests for comment. We can search in net and find the different RFCs. So RFC 3168 represent or specify this explicit congestion notification. As you know, congestion control is provided by transport layer, right? And usually how transport layer understand or the sender understand that there is a congestion using packet loss as a signal. If my packet is lost somewhere, I am not receiving any acknowledgement, that means that there can be some congestion and my packet is lost. That is implicit assumption on congestion. The second method of understanding about the congestion is that using explicit congestion notification. The receiver can explicitly inform the sender that your packet is lost due to congestion or there is congestion. Please slow down your transmission rate. Such a facility is also there in transport layer, and that is called actually explicit congestion notification. So first let us see what is actually ECN, then we will move on to those 2 flags. Okay, so ECN or explicit congestion notification. So usually congestion control is or the congestion signal is a packet loss. Whenever there is a packet loss found out by the sender, my packet is lost, that is actually a signal for congestion. I have to reduce my speed or my transmission rate, otherwise my further packets also may get lost due to congestion in the network. And the second method of understanding about the congestion is through explicit congestion notification. That is, ECN is actually an IP layer mechanism. It's not provided by the transport layer, but it's provided by the IP layer. What the IP layer will do? IP layer will notify the host of congestion. IP, the network layer, can inform the transport layer that there is congestion. How it is happening actually? The TCP receiver can receive congestion signal from IP. The use of ECN is enabled for a TCP connection when both the sender and receiver indicate that they are capable of using ECN by setting the ECE and CWR bits during connection establishment. So initial time at the setup time or the connection establishment time itself, the sender and receiver should agree that we can use this explicit congestion notification. How they will agree that? By setting these 2 flags. You already seen these flags, right? CWR and ECN. Those 2 flags. By setting those at the time of initial connection setup, the sender and receiver agree that we can have a congestion control using this explicit congestion notification method. Notification is done by these 2 end systems. So if ECN is used, each packet that carries a TCP segment, packet in the sense it's the data unit for the IP layer, right? Network layer, Each packet that carries a TCP segment is flagged in the IP header to show that it can carry an ECN signal. So IP header also carries some information to indicate that this segment can carry some ECN signal. Okay, and routers that support ECN will set a congestion signal on packets that can carry ECN flags when congestion is approaching. So in the network layer, main active components are these routers, right? So in case of routers which can support ECN, what they will do? When they find out that there is some congestion approaching, they will immediately set these ECN flags. Okay. So on packets that can carry ECN flags when congestion is approaching, instead of dropping those packets, normally if there is no provision for this explicit congestion notification, it will simply drop the packets to solve this congestion. But here even before the congestion happening is about to approach, it will just set the flags in the corresponding IP packet, and the TCP receiver is informed if any packet that arrives carries an ECN congestion signal. At the receiver side, the data packet will be there in the IP layer, right? So in the IP layer, this network layer will check whether there is some ECN information. Yeah, it's there some information. It will pass on to the next layer, that is transport layer. It will tell the transport layer that there is some congestion information carried by this packet. Okay, so you have to inform the sender. At the receiver only, this ECN notification will be informed by the IP layer to the transport layer. So at the receiver side, the transport layer will be notified by the IP layer. So what the TCP layer and the receiver will understand? Yeah, there is a congestion on the network. I have to inform the sender. So TCP. Now the receiver, that is the transport layer at the receiving machine, uses these flag, ECE flag, one of the flag in our discussion, that is ECE, that is ECN echo, because it received an ECN, right, explicit congestion notification. So it should inform the sender back. For that it will be using this ECN echo. It giving a feedback to the sender that I have received an explicit congestion notification by my IP layer, so you have to reduce your transmission rate. Such a flag will be sent, such a data segment with that flag set will be sent back to the sender. On receiving this special packet or special segment in which this ACE flag is set, what the sender will understand? Yeah, there is some congestion. I have to slow down my transmission rate, and it will inform back the receiver. Okay, the sender tells the receiver that it has heard the signal by using CWR. Yeah, I have understood that there is some congestion. I have received your information, so I am going to reduce, or I have already reduced my congestion window size. So actually congestion window is the number of segments that can be transmitted without any congestion. That is assumption. So a size will be set initially. So based on that only the sender will send the different segments. So I have to reduce my congestion window size to solve this congestion. So this flag will be set by the sender and it will be sent to the receiver. So we can say that CWR is actually acknowledgement for this ECE. Yeah, the response from the sender back to the receiver. Yeah, I have already received your information. I am reducing my congestion window now. And next flag is URG, that is urgent. So URG flag is set to 1 if the urgent pointer is in use. So that is another special interesting service provided by TCP. That is, it can carry some urgent data. Urgent data in the sense when an application has high priority data that should be processed immediately. In such case, the segment which carry this urgent data can be notified by indicating or setting this URG flag. So if this URG flag is set, that means the corresponding segment carries some urgent data, and both its urgent data is there in the data segment part, which is pointed by this urgent pointer. Another field in this TCP segment header, that is urgent pointer. So if URG is set, the urgent pointer point to the starting of the corresponding urgent data. So just for example, this type of urgent information which can allow the user to kill the processes running on the remote machine. In such case, we should not wait for some other process to or some other data to be processed, right? As and when this particular information is received, that process should be terminated, killed. So such urgent data can be indicated using this URG flag. And the next flag is ACK. ACK stands for acknowledgement. So if ACK bit is set, that means this segment carries acknowledgement information. So acknowledgement number in the corresponding segment is valid. Otherwise, so in most of the cases this will be the case because the data fragment also carries some acknowledgement information. But in some case that may not be the case. Only the data will be there in the corresponding segment. So if ACK is 0, the segment does not contain an acknowledgement. So the acknowledgement number field in this case will be ignored. And the next flag is PSH. PSH stands for pushed data. So what is actually pushed data? The receiver is hereby kindly requested to deliver the data to the application upon arrival and not buffer it until a full buffer has been received. So usually for efficiency reason, what the transport layer will do is it will keep the data received from the network layer in a buffer, and it will hand over this data to the application layer only when the corresponding buffer is full. The entire data from the buffer will be handed over to the application layer. But if the PSH flag of a segment is set, in that case the receiver should immediately, the transport layer of the receiver should immediately hand it over to the application layer without buffering it or without waiting to fill the buffer. That is PSH flag. And the next one is RST. RST bit is used to abruptly reset a connection that has become confused due to a host crash or some other reason. So if in any reason, if a machine want to reset the corresponding connection, it will send such a segment which carries RST bit set. Okay, so if the receiver sees that RST bit set, the corresponding communication connection should be abruptly reset. So it is also used to reject an invalid segment or refuse an attempt to open a connection. So such some error or problematic notification will be carried by this RST flag. And the next flag is SYN. SYN stands for synchronization, and this flag is used to establish connections for connection request and connection replay. So if a particular segment carries SYN as 1 and ACK as 0, that means there is no piggyback acknowledgement. So if the SYN bit is used to denote both connection request and connection accepted. In both cases, SYN will be 1. How they can be differentiated? Yeah, using this ACK. If ACK is 0, it is a connection request, and ACK 1, it is a connection accepted. And the next flag is FIN. FIN stands for final. So this is used to release a connection. So if a particular sender is not having any more data, this is the last segment of data, it can indicate the same to the receiver by setting this FIN flag. So when a receiver receives a data segment with this FIN bit set, that means the sender is not having any more data, I can close the connection. But after closing the connection from sender to receiver, receiver can still continue to send data to the sender. That's another connection. And the next field is window size field. As you know, this transport layer provide or transmission control protocol provide both flow control and congestion control. So it should keep a window of segments which can be sent at any time without receiving any acknowledgement. So flow control and congestion control both should be kept using a window. So flow control in TCP is handled using a variable size sliding window. So depending on the current flow, depending on the receiver's capacity and all, this size of this sliding window will be adjusted. And the window size field tells how many bytes may be sent starting at the byte acknowledged. Currently, how many bytes can be sent? That will be indicated by the window size field. And now what's the meaning of this window size field 0? Window size field 0 means no more data can be sent by the sender, right? Yeah, the current window size is 0. But that is also legal. When that happens, actually, the meaning is that the bytes up to and including acknowledgement number -1. Acknowledgement number -1 means the last data sent. So all the bytes up to and including the last data sent have been received in the receiver correctly, but that the receiver has not had a chance to consume it. Maybe the receiver is slow or low-end machine or some any other issue. Receiver couldn't process those data. So for the time being, receiver is not able to receive any more data. Only after processing those received data, it can receive. That is the meaning of this window size field 0. Later, after processing all this data in the receiver can inform back the sender, yeah, now I am free, you can send the data. How it will inform? The receiver later grant permission to send by transmitting a segment with the same acknowledgement number. Same acknowledgement number means, yeah, now I am expecting this data byte, like that. And a non-zero window size field. it will change the window size field into some non-zero value, means that you can send data. And the next field is checksum. We have already seen this checksum in the UDP segment also, right? It is used to provide extra reliability. It checksum the header, the data, and a conceptual pseudo header in exactly same way as UDP. We have already seen that clearly in there. So same thing happens in case of TCP also. But the difference between UDP and TCP in computation of checksum is that, except that the pseudo header has protocol number 6 for TCP. In the case of UDP, it was 17, right? Yeah. And the next one is options field. So far we have discussed different fields which are part of the fixed header part. Now the next is a variable length option fields, and many options are there and most of them are commonly used also. And the options are of variable length, fill a multiple of 32 bits by using padding with zeros. So even if half of a 32 bit is used, the remaining half will be filled with zeros, and may extend to 40 bytes. Up to 40 bytes can be there in a option part to accommodate the longest TCP header. And some options are carried when a connection is established to negotiate between the sender and receiver. Some other options are used throughout the corresponding communication, like that. Just for example, one option is maximum segment size, or MSS in short, and which is used widely to allow each host to specify the maximum segment size it's willing to accept. So depending on the buffer capacity and all, a machine can specify that this is the maximum size I can accept. So of course large segments are more efficient than small ones, right? Because every segment should contain a header. So maximum possible data should be carried by a particular segment to increase the channel utilization, right? To reduce the amount of extra information like headers and all. That is the case. But there can be some host which is able to handle only small segments. For example, small host or with small buffers and all, they have a limited capacity to carry segments. So they will specify that this is my capacity, please hand over such segments only. Like that they can specify using this option. So at the time of connection setup itself, each side, each sender or each machine can announce its maximum and see its partners. Okay. And if a host does not use this option, the default value for the size of a segment will be there. So default size of a segment payload field is 536 data part 11. So any host, they should be ready to accept a segment of this much size, 536 payload plus 20 header. Another option is timestamp option. Timestamp option carries a timestamp sent by the sender and that can be echoed by the receiver. So why we need such a timestamp option? It is included in every pack once its use is established during connection and used to compute round trip time samples that are used to estimate when a packet has been lost and all. So when we send a packet by the sender, it will set a timeout, right? How this timeout actually set up? Based on the round trip time. So how can we measure the round trip time? Using this timestamp. When a sender sends a packet or segment to the receiver and the corresponding acknowledgement is received back from the receiver to sender, that much time is the round trip time. That can be measured using this timestamp field of a segment. So it's also used as a logical extension of a 32-bit sequence number. So that is useful in case of fast connection. So in case of a fast connection, sequence number may wrap around quickly, leading to possible confusion between old and new data. Sequence number wrapping around means, just suppose we are using a 2-bit sequence number for simplicity, 2-bit sequence number. So different numbers that can be uniquely identified as 0, 1, 2 and 3, right? Only 4 different numbers. After 4 segment, the 5th segment also should be numbered as 0, right? Yeah, so first 4 segments, again the 5th segment is also 0. That is called wrap around. Again we are moving to the next sequence number in the same range. The problem here is that if the connection is very fast, first 0 will be there in the receiver. At that time the second 0 segment also may be received in the receiver. So the receiver should be able to identify which one is the newer one, which is the older one. In that case we can use this timestamp. So that is used as a pause, that is protection against wrap sequence numbers. And the next option is selective acknowledgement, or SACK in short. So this SACK lets a receiver tell a sender the range of sequence numbers that it has received. So already there is an option, acknowledgement number. The receiver can tell the sender that I have received this much and I am expecting this sequence number next, right? But if there is some issues like a packet has been lost, in such case the SAK can be used. So SAK supplements the acknowledgement number and is used after a packet has been lost but subsequent data has arrived. Just for example, suppose packet X is lost and X plus 1, X plus 2, X plus 3 are received correctly in the receiver. In that case, what should be the acknowledgement number on receiving this X plus 1, X plus 2, etc.? Still the acknowledgement number will be X, because the receiver is telling that I want X as the next in order byte. It always expecting the bytes in order. So whatever may be the bytes it received correctly after the lost one, always it will tell the corresponding lost sequence number only. So how the sender should identify that only this segment X is lost and the remaining all are correctly received. In such case, it can take the help of this SAC. So it can understand that only X is lost, the remaining is safely there, X plus 1, X plus 2, everything is there. I need to retransmit only X.